Welcome everybody who's coming in. I can see there's 360 of you, so good morning. And welcome to the YouTube folks as well, who are not able to join us at this instant. Welcome back from your break. I hope everyone had an enjoyable break. At the beginning of the break, the weather here in Toronto was outstanding. So nice and warm outside. I was just outside lying on the grass actually for some of Tuesday. Let's get into things today. I'm going to share my screen down here and talk about what is on the agenda. So that's sort of what we're doing. We're finishing off chapter 8. Let me bring up all my Zoom stuff here. Make sure I got my chat. Okay. William was asking if we can use the lever arm trick to solve the torque problems. That's definitely what I'm going to be doing, lever arm trick. So I'll show you how that works. Finding x, which is the distance between the force line and the rotation axis. And then the chapters on the midterm tomorrow are just chapter 8 and chapter 7. Okay, and this is actually, so I was watching Beauty and the Beast over the break with my kids, and this is the Beast, which is that sort of big guy there, and then there's also Gaston, who's like the villain actually. So the villain is this guy with the red shirt. Anyway, this is at near the end of the movie, and you just kind of are really rooting for the Beast at this point. He ends up saving Gaston's life, even though he's dangling him over the edge. And it's quite an interesting static equilibrium problem if you look at it. And in fact, the animators have even taken the arm of the Beast and had him grab onto a gargoyle, which is important because otherwise he would tip. So what we have is, here's the force of the Earth on the Beast, which probably looks like it's a little beyond his, you can put a rotation axis as his furthest support point to the left. Certainly Gaston is way over here. So all of the torques of the gravity on the Beast and the force of Gaston on the Beast are going to be positive counterclockwise torques. The force of the floor on that rotation axis won't have any torque at all. So you need a negative torque. You need a clockwise torque to kind of balance him from tipping. And that would be the force of the gargoyle on his hand there, pulling him towards the right. So I think I do want to start off with doing some static equilibrium problems. I had been wanting to do this ladder problem for a while. So why don't we get started with that? So a uniform ladder, this is one of the sort of canonical problems of static equilibrium. It's good to know how to do. You got a ladder that's leaning against a wall, and it says here that the wall is frictional. So I'll put here friction equals 0 up here at this point. What is the minimum coefficient of static friction between the ladder and the floor needed to prevent the wall from slipping? So what you're going to have is some force of static friction right there on the floor. We'll also have some sort of normal force, normal of the floor on the ladder, the static friction of the floor on the ladder. We'll also have this force right here, I guess the force of gravity of the Earth on the ladder, which will be, it's a uniform ladder, so that's going to act at the halfway point. And you can have, the wall doesn't have friction, but it can have a normal force. There's actually two normal forces in this problem. The normal force of the wall on the ladder and the normal force of the floor on the ladder. So this is, right here is the wall, W. This is the floor. So L is the ladder, F is the floor, W is the wall. And what you're trying to find here is mu sub S between the floor and the ladder. Floor and ladder. Okay. Let's try it. So in my simplifying diagram, I'm going to draw sort of this extended free body diagram of the ladder. I'm going to define the system as the ladder. So let's draw a force diagram for that. Here is going to be the N of the wall on the ladder. There's going to be, again, force G of earth on the ladder. There's going to be this force of static friction of the floor on the ladder. And there's going to be this, well, that's not a force in that direction, I think. Let's erase that. It's going to define my XY axis, but let's just finish by putting all the forces, and there's going to be this normal force of the floor on the ladder. I think that's all the forces that are acting on it because there's no friction at the top and there's nobody standing on the ladder. So let's define axis of rotation to be the foot. Now it's a static equilibrium problem, so you can put this axis wherever you want, but there's two forces acting on the foot. And so sometimes when I'm choosing axis of rotation, I put it somewhere where there's more than one force so that they, when you're doing the torques, they'll both be zero. Just fewer things to keep track of. I'm also going to define y to be up and x to be towards the right. And L is the length of the ladder, which it doesn't say. So, okay, so assume static equilibrium. That's how all these chapter 8 static equilibrium problems really work. You're gonna have to do something like this tomorrow. So what you can say is the sum of the x forces is equal to 0. The sum of the y forces is equal to 0. And the sum of all the torques is equal to 0. So the x forces are going to be the normal force. There's two normal forces, so we're going to keep track of them with the subscripts. The wall on the ladder minus this static friction that we're trying to find. And then the sum of the y forces is the normal of the floor on the ladder minus, I guess it'll be mg. M is the mass of the ladder. And then the torques is going to be, if we have the axis of rotation, there'll just be these two forces here. So it's going to be the torque due to gravity plus the torque due to the normal force of the wall on the ladder. Okay. Because the forces that are acting on the rotation axis do not provide a torque. So the way I'll do this is I'll find this kind of, if this is L, and this is theta right here, and this is the normal force of the wall on the ladder. So this is theta up here, sort of by the Z rule. Then this distance is the lever arm x. So you would say that the torque of the normal force of the wall on the ladder is equal to the normal force of the wall on the ladder. It's going to be clockwise, so it's negative. Oops. Negative times this distance x, which will be, well, it says right there, 2 meters. Okay, 2 meters. And then the torque due to gravity will be positive, and it'll be the mg times the, again, the x distance right here, which will be half of 1.5. So I'm going to call it 1.5 over 2. And that one's going to be plus. And what we're going to do is assume that the static friction force is Fs max is mu s times the normal force of the floor on the ladder, because it's just about to slip. So what we've got here, if we want to label these equations, we can call the x one, we'll call that 1. The y one we'll call 2. The torque one we'll call 3. And then this Fs equals Fs max is mu s times the normal force. We're going to call that 4, equation 4. So equation 4 is telling us that mu sub s is equal to F sub s divided by the normal force of the floor on L. And 2, equation 2 is telling us that the normal force of the floor on L is equal to mg. That's just balancing the y forces. So we can plug that into here. Equation 1 is telling us that the static friction force is equal to the normal force of the wall on the ladder. So we can plug that into here. So that means that the mu sub s is equal to the normal force of the wall on the ladder divided by mg. So all we need to do is use the torque equation 3 to find the normal force of the wall on the ladder. So 2 times the normal force of the wall on the ladder is equal to 0.75 mg. So the normal force of the wall on the ladder is equal to 0.75 divided by 2 times mg. So mu sub s is equal to 0.75 times mg divided by 2 times mg. The mg's cancel. And you get 0.75 divided by 2. So you get 0.38. So this is the minimum coefficient before it slips. Before slipping. Okay, and it seems reasonable. It's less than 1, for example. So the ladder probably doesn't slip. To Drew, I think, yeah, the torque of the wall on the ladder is negative because it's clockwise. The angles didn't come into play because I used the X, this idea of the lever arm. Thea, you've had your hand up for a while. How's it going?
Oh, hi. Can I ask a question about the midterm assessment 4?
Yes, please.
Like, I noticed that we didn't do any examples like this for center of mass, or we didn't have any specific rubric for center of mass. Does that mean we're not focusing on center of mass in this assessment, or do we have a more specific rubric for that?
Yeah, no. So it's just going to be a static equilibrium problem from this.
Okay, good. Thank you.
Good question. Ethan?
I have a question about equation 3.
Yeah.
So I noticed that the torque, the L is based on 2 meter and 0.75 meter, but that's not like part of the ladder. So shouldn't it be like 2.5 for the top force, and then like half the ladder length for the gravity?
So what I've done, this is a bit tricky, is I have taken, could draw it maybe in a different, it's a really good question. I have figured out these torques based on the distance between the force line and the rotation axis. So this distance is what I call X, okay, which was the lever arm. So the torque just equals the force times X. In this case, the normal force times that distance X. Okay. And then for this gravity one, same thing, X is going to be here in this case. The distance between the any big line that goes through the position where the force is and is applied and that is parallel to the force, the distance between that force line, the perpendicular distance or minimum distance between the force line and the axis rotation is what I call X. And those ones you can just read straight off this diagram, and that way you don't even need to know what the angle theta is.
Okay, thank you.
A bit of a shortcut there. Great question. Emanuela, did you have a question?
Hi. I had a question about black holes, and same as the other girl that just asked right now. So we're not expecting to see that because we didn't really do examples of that, right?
Right. Which chapter was the black holes? I'm trying to remember. This is
That's
from,
the very end of chapter 7. We didn't even go through the example in class, but that's them in the textbook.
yeah, that's true. I think it is, it's important stuff, and maybe it might show up on the final exam because it is part of your reading. But yeah, tomorrow's test does not have anything on black holes.
Thank you.
Good question. Okay. Excellent. Okay. So what's next here? I think I'm going to do a couple poll questions here. What that was. Okay, so let's launch a poll. A construction worker of mass MW sits 2 meters from the end of a steel beam of mass MB, as shown. I'm going to do 2 questions on this guy. The tension in the cable is T for tension. The wall exerts a normal force on the beam and an upward force. It's sort of, that's where like the hinge would be, I guess. So X is to the right, Y is up. The pivot or the axis of rotation is the point where the beam touches the wall. What is the normal force lowercase n of the wall? So the pivot, we'll call that axis of rotation. So I've given a hint that this normal force, you don't even need torques for this. You're gonna try to just balance what the X forces are, because it's static equilibrium, so it's not accelerating left or right. Give you 30 seconds. Please click in. Okay. And then I think next is we're going to try to find the F1 force. Going once, going twice. So 53% of you, 194 who voted for E. And I think that's what I liked. So basically all you're doing is you're saying that the sum, the sum of the F X is equal to 0. So that's going to be equal to N. These are all vertical, minus, so what you have to do is at some point take your T and split it up into, this will be, here's theta, which is 30 degrees. This will be negative T sub X, and this will be positive T sub Y. So this is going to be minus T times cosine of 30 degrees. So then you just solve that out, and you get N is equal to T cos of 30. So next question I've got is, what about the force F1? My hint there is that it can't accelerate up or down. You don't need torques for this one either. Hopefully all of you can see these poles. Okay, so please click in on the poll. Once, going twice. And you can see 289 of you, 76% voted for C. And in fact, it's exactly right. That's the one I liked as well. So well done. So basically, yeah, same sort of thing. The sum of the f sub y is equal to 0. And that's equal to F1 is up minus the mass of the beam times G minus the mass of that worker times G. And then this is going to be plus T sine of 30 degrees. And then you just kind of solve this all out. So F1 comes, add all those things to the other side. F1 is equal to positive MB times G plus MW times G minus T sine 30. So that's C when you rearrange a little bit. So I'm going to try to solve something similar to this. Let's say you get this on the test tomorrow. A uniform steel beam of length L and mass M1 is attached via a hinge to the side of the building. So there's the building. Here's the hinge, I guess. We'll put it, here's your beam, we'll draw it. Length is equal to L. Okay, so it says the uniform. So basically I'm going to put this sort of M1 times G and this distance L over 2 from the hinge being like that. Okay, test by hinge. The beam is supported by a steel cable to the end at an angle of theta. And it says as shown, but I didn't draw it here, but let's just put it there. Through the hinge, the wall exerts an unknown force F on the beam. So I can put that kind of here. A workman of mass M2 sits eating lunch at distance D from the building. So this is very similar to what you just did. Here is sort of this M1G. And that's D to go to all the way to here. So find T, the tension in the cable. So T is equal to question mark. And find Fx, the x component of the force exerted by the wall on the beam. So Fx equals question mark. So that's part A and part B. We're going to define y to be up, x be towards the right. We're going to define the system is equal to the beam. And what I'm going to do here, similar to what we did before, is that the normal force, the workman is in equilibrium. So there's sort of a three-step process here. The workman has a downward force of gravity of the earth pulling the workman down, which is M1, M2 times G. And then to put the workman in equilibrium, the beam has to push upwards on the workman with the same magnitude force, M2G. And then by Newton's third law, the workman is pressing down on the beam with a force of magnitude M1G. So normal force of workman on the beam is equal to M1 times G. I'm just going to write that as assumption. So the hinge is the axis of rotation. We're going to again assume static equilibrium. Let's try to draw our little force diagram. I've got, let's put two forces here, Fx of the, I guess, the wall on the beam or the building or whatever it is. Fy, probably up, of wall on beam. We've got this force down, the force gravity of Earth on the beam. And we've got the normal force of the worker on the beam acting down. And we've got this tension force acting up of the string on the beam. Or cable or something like that. Cable. Okay. So, and what we could do with this tension, we have to do this, is try to figure out our x to the rotation axis. So if the rotation axis is all at the very left end, and this is x, and this is your angle theta, then the torque due to the tension is equal to T times x. So the torque due to the tension is equal to T times L times sine theta. So you need to do that at some point. So for step A, you say that the sum of the torques is equal to 0, which is equal to TL sine theta is the positive torque, minus M2 times G times D, minus M1 times G times L over 2. So one negative torque from the workman sitting on the beam and another negative torque from just the beam itself, the gravity on the beam. And so you can solve that out for tension. T times L times sine theta is equal to M2 GD plus M1 times G times L over 2. So tension just equals M2 times G times D plus M1 times G times L over 2 divided by L sine theta. And this question doesn't actually give you any numbers, so I think that's just it. And then for part B, you're asked for that Fx. So let's do the sum of the Fx forces is equal to 0. So it's Fx that you're trying to find minus T cos theta. We already have T, so Fx is just equal to, running out of room here, T cos theta. Let's shift this over. Finish it up. I think that's it. You just say Fx is equal to, I'll just rearrange things a little, cos theta divided by L sine theta times M2 times G times D plus M1 times G times L over 2. And so the weird thing about this is that there's no numbers to plug in, but that could happen. One thing you can do, Akina suggests that maybe you could try limits. So maybe as theta goes towards 0, what's interesting is that sine theta goes to 0, so the tension will approach infinity. And also F sub x will approach infinity. So there's, again, there's a sine theta on the bottom. So this makes sense. You can't support the beam with a cable that is just parallel to the beam. The whole thing will just fall. So it makes sense that you would need a infinite tension. And then the other thing that I could say, another thing is that as M1 and M2 increase, and all the other things are kept the same, the tension and Fx increase. So that makes sense too, because those are on the top. Okay. What's everybody doing out there? Maybe Ilian, did you just want to unmute?
Hi, how are you?
I'm good.
I had a question about the ladder problem, but I suppose it's kind of relevant here as well.
Sure.
So when you find the torque, which is the force times the length, the length that you're multiplying always the perpendicular length? Because earlier you had the ladder was the torque was the force times 2 meters, but the 2 meters was the length of the wall.
Right, but that was the perpendicular length, I think. It wasn't the diagonal, right?
Yeah, so it's always the perpendicular length that you're multiplying by force for the torque?
Yes. I mean, there's two ways of doing it. So you can do the diagonal length times sine theta, like they do in Atkina, or you can just use the perpendicular length, which I call the lever arm. So I call that x.
Okay, so how come it would be the, like, I guess just for a intuitive understanding, how come it would be the perpendicular length as opposed to like the parallel length, if that makes sense?
Yeah, well, so just intuitively, I think that's the length that gets something turning. Like if the tension was pulling directly towards the rotation axis, then that perpendicular length would go to 0, right? And it doesn't turn it. You kind of need that perpendicular length to be as great as possible. Like if you're going to open a door, for example, you would pull the door perpendicular to the rotation axis, and that's to give you the maximum torque. So to maximize that torque, you always want to have perpendicular distance be as big as possible.
Okay, thank
That's
you.
what's causing the rotation. Yeah, good questions. And then Josephine, did you want to unmute?
Hi, can you hear me?
Yes, I can.
I also have a question about the latter question.
Yeah, sure.
Can you go back to the solve and evaluate section?
Is it here? Is this right? Yep. This question.
Okay.
Right.
So for the top right of the screen,
Yeah.
I understood like it until you got to this part. How did you come up with those two equations?
I think, did I just solve out? So Fs is the normal force on the wall. That comes from balancing the x components of the forces,
Right.
which is kind of what we were doing in the poll, right? Is that there's always three equations in static equilibrium. Balance the x forces, so no torques at all. Balance the y forces, no torques at all. This is sort of chapter 3 stuff. And then the third equation is they have to balance the torques, and that's more of a chapter 8 business.
Okay, so if there's no friction in the y component, then how did
Right.
you get that for the y component?
For the y component, all I knew was that the normal force of the floor is equal to mg. The second one is the y. The first equation is in the upper right-hand corner is from the x balance, and equation 2 is from the y balance.
Okay, I was just confused because there's no friction in the y, so I don't know how you got the mu there.
Yeah, the mu, so the whole equation for that comes from just the fact that it's just about to slip. That's a fourth equation actually, which is that the whole thing is just about to slip. So I set the Fs to be equal to Fs max.
Okay, so even though like there's no friction in the y direction, that's still included in the equation?
Yeah, because it's when you're doing the x friction on the floor, what's causing, I guess, or what's giving the normal force for that is the y component of the force. I see what you're saying. You've got n in the y direction, which is affecting the x direction friction, right? So when you say the equation for friction is mu sub s times n and the friction force are always perpendicular to each other in that equation.
Oh, okay, got it. Thanks.
Okay. Yeah. Great questions. Okay. How are we doing? So there is one more thing that we wanted to cover today, the last sort of section of chapter 8, which is all about equilibrium and the stability of equilibrium. So then there's something to do with the base. So if you're on a subway train, which I haven't been on a subway train since March actually, but if you're standing on a train and it's moving, one trick that you may have figured out is that you can stand sort of like almost like you're skateboarding, so that your legs are one foot is towards the front of the train, the other foot is towards the back of the train, and you want to put your feet kind of farther apart from each other. So that what happens is that, assuming the stance, you increase your area of support, which is the area of contact between the object and the surface that it's supported by. So if you're accelerating towards the right here, then your center of mass will, if you lean backwards a little bit, will still be over your foot. Whereas if your feet are close together, you could just tip right over. As soon as your center of mass is beyond or, is no longer above your area of support, that's when you tip. So the tipping point is right when your center of mass is exactly above your area of support. That's sort of one basic idea. So the location of the center of gravity or center of mass is important for stability. If you draw a line straight down from the center of gravity and it falls inside the base, then the thing is in equilibrium. If it falls outside the base, then it'll fall. So this is the Leaning Tower of Pisa. the center of gravity is still above the base, and that's why the whole thing doesn't fall over. But if it keeps tipping, so that that goes outside the base, then the thing will tip over. I had to actually see what. Yeah, well, we'll finish up the lesson basically. So stability, an equilibrium is stable if a slight disturbance from equilibrium results in some forces that tend to bring it back to equilibrium. So example, this cone that's sitting on its base, if you were to give it a slight tap to the left to make it tip, or a slight tap to the right to make it tip, it'll tend to fall back onto its base again and won't just tip right over. So this is, cone at base is stable. An equilibrium is unstable if, when you give it a slight tip, there's forces which cause it to accelerate away from equilibrium. So example is the cone that's on its tip. You give it a little nudge to the left, it'll continue falling to the left. It'll accelerate away from equilibrium. So you can imagine both of these things being balanced. So they're in equilibrium, they're not accelerating if it's exactly balanced, but one is in a stable equilibrium and one is in an unstable equilibrium. So we got a few polls here. Let me run this one first. The centers of gravity, so the center of mass is, I guess, same thing, of these three trucks are shown by the X's. So somehow people have loaded the backs of these trucks in some weird way with a whole bunch of boxes, so that the center of mass of the whole truck is of A, B, and C are shown by the little red X's. So which of these trucks will tip over? A, B, or C? Or do you think D, all three of them will trip over or tip over, or E, none of the three will tip over? What do you think? Lauren, I'm not sure what's going on here, but the trucks are A, B, and C. Okay, you got it. It's right on the trucks. Okay. Just another 5 seconds or so to click in. You kind of have to judge this a little bit by eye. I'm going to turn off the voting here. But 73% of you, 280, voted for A. I think that was what I was going for too, is that if you look at B and kind of try to draw a line straight down, I think, it's a little hard to do on my screen here, but I think it falls like just on that corner, so it's not going to tip. And certainly for C, it definitely falls within the base. So this is the base. I think that for B and for C, if you draw a line straight down, it's within the base. But if you do it for X, then it's here. So this will have a torque around this point and the whole truck will tip over. That's just the basic idea. Let's do a quick example. Refrigerator is 2 meters high. So let's draw a little not tipped. 2 meters high, 1.4 meters wide, on a flat floor. By what maximum angle can it tip sideways and still not fall over on its side? So if we draw it not tipped for a second. It's 2 meters high, like that, and it is 1.4 meters wide, 1.4 meters. And what we can do is make an assumption, assume the center of mass is at the geometric center. So like half of 1.4 away from the left and half of 2 meters away from the floor. So what we're going to do is do the maximum tipped. Right here. It's a little hard to draw though. I'm going to draw it. You have to draw it so that the center of the fridge is directly above the sort of the pivot point. Okay. So we're going to tip it up from the floor, some angle theta like that. And then what we've got is that this distance from here to here is 2 divided by 2 equals 1 meter. Makes sense because it's halfway up. And then this distance right here is equal to 1.4 divided by 2 is equal to 0.7 meters. And so I'm just going to draw it out here. I know I'm supposed to be doing equations now, but I think the way this works, if this is theta, then this is 90 minus theta. And so this is theta up here. And this distance is the 1, and this is the 0.7. 1 meter and 0.7 meters. So now you just use geometry. I think that tan of theta is equal to 0.7 opposite divided by adjacent 1 meter. And so you just do theta is tan to the minus 1 of 0.7 over 1. So I got 35 degrees when I did that in my calculator. And I don't know how to evaluate, but it's less than 90, so that's good. Everybody doing okay with this stuff so far? Omar, did you have a question?
Yeah, sorry. I had a quick question about torque equation.
Yes.
This is a two-part question. So how do we know when to use sine or cosine for the torque equation? And also sometimes the textbook, when it's doing these sort of questions, it adds, like say an angle, we have 30, and then it adds a 90-degree angle to it as well. So it's like 120. So I'm just confused on the sine, cosine, as well as the how to get the degree.
Okay, so that's a great question. So it's always going to be, whenever it's going to be sine, if you're using theta as the angle between the force vector and the vector, I guess the length vector, which is between the rotation axis and the point where you apply the force. So you've got that lowercase l vector, which starts at the rotation axis and goes out to wherever you're applying the force. And you've got the force vector. If you connect those two vectors tail to tail and measure the angle between them as theta, then the torque is that force times L times sine theta.
Right. So it doesn't matter which side the force is pushing. It could be from either up or down or from side to side.
Right. If it's so, yeah. If the force is perpendicular to L, then theta is 90, and sine of theta is 1. I mean, the only thing you also have to worry about is that F times L times sine theta, that gives you the magnitude of the torque. And then if it's counterclockwise, it's positive, and if it's clockwise, it's negative. So you have to put the sign on based on your actual diagram.
Okay, great. I just have one
So,
more quick question, if I
sure.
can ask for chapter 7.
Mhm.
If an object is not accelerating and it's at constant speed, we remove the kinetic energy from both sides of the work bar chart diagram, right?
Well, I wouldn't. I mean, that's a good question, because this actually happened, I think, when something was sliding at a constant speed down the ramp. If it's constant speed, that means that the kinetic energy is constant. And so that's true when you represent mathematically, you'll subtract the same constant kinetic energy from both sides. But I think when you do your simplifying diagram and you've drawn your little bar charts, there is a non-zero kinetic energy on both of them, right? Like if there's a bit of kinetic energy at the beginning, same amount at the end. It's just that they're the same. It doesn't change. Does that make sense?
Thank you. Yeah.
Sure. Okay. Great questions from Omar. And Jerry, did you have a question?
Hello, Professor.
Hi.
Hi, I just have a question about the ladder question. Like, can you go back to the first slide of the ladder question?
Sure can. Just keep. And we're going to do a couple poll questions before the end here, but like this one?
Yes. So just at the bottom right, for torque G, why is it mg times 1.5 over 2?
Great question. So I think that the 1.5 over 2 is that letter X. So we were talking about L sine theta. L sine theta is X, where X is the distance between the force line, which here is a vertical line dropping straight down from the center of mass, and the rotation axis. And I've defined the rotation axis to be where the ladder touches the floor. So if it's 1.5 meters from where the ladder touches the floor to the wall, then half of that distance is X, the lever arm.
Okay.
It's a really great question. You see it? I did it a little
Yeah,
quickly.
I kind of see.
That's also equal to L sine theta, but I just find it so much easier to try to do a lever arm, where X is the distance, the perpendicular distance between the force line and the axis of rotation.
But isn't like the perpendicular distance? Oh wait, never mind. Okay, I got it. Thank you, sir.
Got it?
Yeah.
Okay. Again, these are great questions. Okay, let's do a couple more polls. I want to do equation jeopardy. Not equation jeopardy, stability jeopardy. In honor of dear Alex Trebek. I actually, one of the things I was doing as well on the break was watching Jeopardy on Netflix. So reruns of it. Okay. So this is where we give you the answer and you have to give the question, right? It could look like this. And so here's a picture of either stable equilibrium, neutrally stable equilibrium, unstable equilibrium, or metastable equilibrium. Which do you think a ball sitting on a flat floor is? So this seems a little bit mysterious. I'm going to go through the other three. So you can take a wild guess. And then I'll show you what the pictures look like for all four. Okay. 5 seconds. 4, 3, 2, 1. So this one, yeah, this was supposed to be B. So 29% of you voted for this. Is called neutrally stable equilibrium. Okay, because if you give it a little bump, it doesn't accelerate away from equilibrium, but it also doesn't accelerate back towards equilibrium. So it's called neutrally stable. It's stable, but it's just still stable. Let's do another one. So now you have a ball, which is the bottom of a valley. Let me give you 10 seconds to click in on what you think this one is. Five seconds. Okay, you guys got it. This is a stable equilibrium. In this case, what happens is that if you push it a little bit to the left, it accelerates towards the right. If you push it a little bit towards the right, it accelerates towards the left. It always wants to get restored back to its equilibrium. What about a ball that's on the top of a hill? Okay, another 5 seconds. Okay, Yeah, you guys got it. This is called unstable equilibrium. If you perturb it a little to the left, it accelerates away towards the left. If you perturb it a little to the right, it accelerates towards the right. It's always trying to get away from equilibrium. And what about, what would you call this one? It's a little valley, but the valley is at the top of a hill, sort of like a crater or something. Okay. And that one is definitely metastable equilibrium. Okay, I've kind of run out of time a little here. I do want to just quickly say before I run away from you here, turn off the video, there's going to be 2 problems tomorrow night that you solve using the 4-step method. The solutions must be in your handwriting and written upon the answer template sheet or something very similar, in the 4-step method. You'll see both the problems at once, starting at 8:10 tomorrow night. One will be from chapter 7 and the other will be from chapter 8. You'll get an email from Crowdmark at this time, but I'm also going to post a link to the exact same thing under Quarkus, under module 4. So you got 30 minutes to write up your solutions to both, and then 5 minutes to get your images uploaded onto the Crowdmark. So all your uploads should be completed by 8:45. 35 minutes after the start time, actually. Your images should ideally be PDFs or JPEG images. Worst case scenario, if Crowdmark is really failing you, you could attach your images to an email and email it to Physics 131 Fall, again by 8:45. But please only do this if Crowdmark fails. That's otherwise we'll clog up April's email box. On Wednesday, I'm going to be starting in on chapter 9 on rotational kinematics. So have you ever wondered how do figure skaters spin so quickly? Thank you very much. I'm going to turn off the recording and then go to questions. I'll see you guys tomorrow night, or I'll see you on Wednesday.